Hello everyone. So today we will study quicksort, which is a sorting algorithm which is of exceptional interest in the computing community as a whole. Okay, so this is a kind of a weird reason that why it will be exciting or interesting algorithm, where the worst case running time of quicksort is theta n square. Okay, so that's not really a very exciting thing, as I said. So, but the very important and nice thing about quicksort is that the average case runtime, in average, it takes like theta n log n time, which is pretty good. And that average case, I'll show you at the end during the analysis, that happens for a pretty many number of elements or element organizations, you can say. So when I show you, I'll explain you more. But this theta n log n average case time is also of even more importance because the constants involved in this theta n log n are very small. So for all practical purposes, quicksort is a very good algorithm to deploy for sorting. Another thing is that quicksort is an in-place sort. Okay, like merge sort, you do not need extra space for merging elements, so it is just doing in place. And another thing is that for virtual memory kind of environment, also quicksort performs very well. So overall, seeing everything like the very good average case runtime, small constants, and in-place sort, quicksort is a very lucrative alternative to other sorting algorithms. Okay, so let's see more about it. Quicksort was proposed by Tony Hoare in 1962. Okay, so it's a divide and conquer type algorithm. So and then as I said, it sorts in place. It's a very practical algorithm with little bit of tuning. So as I said, quicksort is a divide and conquer algorithm. Let's see what are the divide and conquer features it has. So what does it do? It works on partitioning the input array. This is the input. Partition input array into two sub arrays around a particular pivot element, which is, suppose this is x, such that elements in the lower sub array are less than equal to x and elements in the upper sub array are greater than equal to x. So I know that you will say less than equal to, greater than equal to cannot happen at the same time. What I try to mean, if this is less than equal to, this is greater than, or this is less than, this is greater than equal to. I'm just trying to keep things simple. Okay, this is just see it from a high level. And so this looks something like this. Okay, pivot element will be here. This is, suppose this is the pivot element, and the array will be organized in such a way using this partition subroutine or the partition procedure, so that in the left side of x will be all elements which are less than equal to x, and the right side of x will be all elements which are greater than equal to x. Okay, so I hope you understand. So after divide, the next step is the conquer. So you recursively sort the two sub-arrays. I'll show you how you recursively sort the two sub-arrays. Actually, the partition procedure itself will continue recursively many times until the array is completely sorted. I'll show you with an example. Now the combine, there is nothing to combine because at the end of this conquer procedure, the array is already sorted. So the combine is actually trivial, just the namesake. Okay, so now after we studied what is a quicksort algorithm and how it operates, like partitions the sub-array into two parts repeatedly to get it sorted, we will try to see what this partition is all about. Okay, so the partition is a subroutine which works in linear time. Okay, linear time means theta of n. So partition subroutine does exactly what is said here. Okay, that see that suppose this is an input array. The input array is A, and the first element is P and the last element is Q. Okay, the first element of the input array is P and the last element is Q. So the array looks like this: A, P to Q. Now you see X is the pivot element, which is actually we are choosing AP. That means the first element of the array we are choosing as a pivot. So now when we study quicksort, we talk a lot about things like how to select the best pivot element, because the entire sorting actually stands on how to select the best pivot element. Some places you will find that the first element of the array should be the pivot element. Some places they will say, okay, the last element should be the pivot element. Some places they will say the middle element will be pivot element. Doesn't really matter, okay? So we will talk more about it later. But initially, let's assume that we just choose the first element to be the pivot element. Any element you can choose to be the pivot element, and the index of the pivot element, like the first element, this is the first element, okay? P is the first element. So we just store the index in the I. There is a first element. We store in a variable I. Now we have another variable j, which is from p plus 1 to q. That means I is the pivot element, I is the index of the pivot element, which is the first one. And then from the second element till the last element, I go through, record through them, and using a loop variable, which is j, using a for loop. Now we check whether the next element is less than x, okay, less than the pivot element we have chosen here. If aj is less than equal to x, then we swap those two elements, okay. So this is C, then and I is increased by 1, and with that new value of I, the current location of I, we exchange ai and aj. Let's show it with an example. It will be much easily understood. So this is the invariant of the quicksort, okay. The invariant is any time in the progress of the quicksort algorithm. So suppose, as I said, the pth element, the first element we have chosen as the pivot, okay. So this is the pivot element, and then from the pivot element will be such that after the pivot element, you see the I is this one, okay. So this is actually I, and the I will be incremented in this direction for all elements which are greater than x, okay. So if we find an element greater than x, then the I is incremented, otherwise I stays in the place. So that's the, let's see with this example, that here this is the array 6, 10, 13, 5, 8, 3, 2 and 11, okay. So now you see I have set up, this is the first element AP, this is the second element AP plus 1. In that way we go to AQ, okay. So the first element I set up as I, and like we said here, I has the index of P, and J is the next one, P plus 1 to Q. J will kind of check through them. So after I set these two loop variables, I check, is AJ less than x or the pivot. See, aj less than equal to x. No, aj is not less than equal to x. This is 10 and the x is 6. So we increment j. So the new j comes here, okay. So the new j will be this one, okay. This is the new j. Now we again check, is j less than aj less than equal to x. Aj is 13 and x is 6, okay. This is x. No, it's not less than. So j again incremented to 5. Here we see aj less than equal to x. Whenever we find aj less than equal to x, what we do, increment I to be I plus 1. So the new I is this, okay. So the I is incremented, and what I do, I swap ai and aj. That means I swap, so let me delete this just for the writing the new array. So the new array is 6, this is the pivot element, 10 and 5 are swapped, okay. This is 5, this is 13, this is 10, and they I'm not writing them at this moment because I will continue. The j has not finished. So now this is the new I, okay. At this moment this is the new I. So this is the new position of I. This is x, the pivot element. You see x remains here. I suppose I create another border here, and the remaining is the position of j. Now the j's current here, j, once it's swapped, j will change to 8. So these elements have not been checked yet. So that was the thing in the invariant we say, at any moment the first element we set as the pivot, and this there will be a set of elements which are less than equal to x, and this partition will grow with the value of I growing, and there will be another set of elements which are more than x, which will be demarcated by j, like j is currently here, we are checking, and then there will be set of elements which are not checked yet. Okay, so they will be with the increment of j, we'll keep checking them. So the invariant is valid at this stage because these conditions are holding. There is set of elements which I know which is less than x, there are set of elements which I know are greater than x, and there are set of elements which has not been checked at this moment. Okay, now j is 8, which is more than 6. So this partition grows, so j grows, j comes to here. Okay, when j comes here, we check whether this one is less than the pivot element, which is 6. Yes, it is less than. So what I do, I increment the value of I. So the new I comes here. Okay, new I comes here, and when I comes here, I have to swap aj with ai. That means what I do, I change 13 with 3. Okay, so I just, it's easy, I change 13 with 3. So now you see this is 8, this is 13. Okay, this is 2, and this is 11. Now you see this partition grows. This is the partition for I. This element which are less than equal to x, this is growing, and this j is now 3 has been considered, so j goes here. Okay, so j's these are all the elements which are more than equal to x, and this partition also grows with j. Now j is pointing, aj is 2, and which is less than the pivot. So again I has to be grown. I will come up to here. Okay, I is now here, and we have to swap 2 with 10. So now what we do, we swap, we bring 2 here. So this is now 2, and 10 goes here. You see, 10 goes here. So now this is the new value of I is this. This partition has grown, and the new value of j is coming to here, to 11. Now 11 is definitely not less than the pivot. So there will be no exchanges with ai and aj. But because there is no more element, this is the qth element, the last element, what we do, exchange ap with ai. Okay, so exchange ap with ai. So ap is the pivot element. Okay, p with ai. So now ai is 2, and so now the new array at the end of this round is this is 2, 5, 3, and 6, and then 8, 13, 10, and 11. Now one round is finished because j has finished checking up to the last element. Now you see what is happening. So there is this list of elements. So here this group of elements are less than the pivot. Okay, less than 6, and this group of elements are more than, greater than 6, less than 6. Okay, less than, greater than. So you see the pivot is in its correct position now. Correct position. Pivot is in the correct position. Okay, so in this way, now there are two sub-arrays. You see, suppose this is the position R. Just assume this is the position R. So these elements are like, suppose from the first element to the, suppose pth position to the R minus 1. And these elements are like R plus 1 till qth position. So now the array is divided into two sub-arrays at the end of the partition, and this is a one sub-array, this is the another sub-array. Now these two will be again undergoing the same procedure of partition. So now you see how this code will be written. So this we come this side. So this is the pseudocode. Quick sort with an input of A, P, and Q. if p less than q, the starting element is less than the ending element, which was happening here, 6 is less than 11. So then r is returning the partition's position. A, P, Q will return the r. As I said, this is the position r. So then quick sort again will be occurring on A, P and r minus 1. So as I said, A, P and r minus 1, and this part is A, r plus 1 till q. You see, again we do quick sort. Quick sort is nothing but repeated partitioning. And when you do quick sort, the partitioning again on this array, this will be even more sorted, and this array it will be even more sorted, and in this way it will keep dividing until the whole arrays are sorted. Okay, so after every time you run one iterations, the pivot element will be in its position. Similarly here also, if you run one iteration, the pivot element will be in its position, and then there will be two more subarrays, and in this way after every iteration one element will be in its position. Finally the complete array is sorted. Okay, so then we will, I hope you understood the basic idea. So we talked about what is quicksort, what are these advantages, and we said how quicksort operates using divide, conquer, and combine procedure. We said that quicksort is depending on a linear time partition subroutine, which is actually dividing the array around a pivot in such a way that after every time partition subroutine is executed, one iteration is complete, the pivot element in its position, and all the elements less than pivot are on the left side, and all the elements greater than pivot are on the right side. So if we keep doing this recursively until the entire array is sorted, then we give the partition subroutine, and we explain the invariant, how they're at every moment during the quicksort procedure there will be the pivot element, a set of elements which are less than equal to the pivot, a set of elements which are more than equal to the pivot, and the elements which has not been identified yet. Now at the end of the partition procedure with the AI, we change the pivot so that the pivot element is in its correct position, because pivot element is actually in the boundary of I and j. Okay, I is the set of here is the set of elements which are less than x, here is the set of elements which are more than x. So the boundary element will we exchange it to place the x the pivot in the correct position. And then we explain the entire partition procedure using an example, and after the example we show the entire quicksorts subroutine, the recursive calls. Okay, then we'll discuss the complexity analysis.